Hi, everyone. I'm Marie Diener-West. I'm a professor in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. I'm happy to be with you today to talk about an introduction to logistic regression.
In the first part of this session on Introduction to Simple Logistic Regression, we conducted a chi-square test and concluded that receiving vitamin A was not associated with the risk of death. In the second part of this session, we will now apply a simple logistic regression analysis to reassess this same association. In case you have not viewed the first part of this session, I would strongly recommend that you first see part 1 of this video and then come back to view this video later.
Or we can perform a simple logistic regression, and that's what we will do. So first, let's take a bit of a sidestep to overview generalized linear models, or GLMs, which are a way that allow us to express the linear relationship, so important word, linear or straight line relationship between a response y and one or more explanatory variables, the x's or covariates. So our goal with generalized linear models is that we have some function of the expected y that we can write as this straight line relationship, beta naught plus beta 1 x1 plus all the way through plus beta p xp. The betas, the regression coefficients for the x's, are what express the relationship between the covariate of interest and the outcome. So you have already seen linear regression as a form of a generalized linear model. So here, the response y was continuous. There was an underlying assumption that the response variable followed a normal or Gaussian distribution. And the regression coefficient interpretation was the change in average y per unit change in x. In other words, one way of saying that is that it's the rise divided by the run. But we'll be looking at logistic regression as another form of a generalized linear model where the outcome y is binary in nature, follows an underlying binomial distribution, and we will see that the regression coefficient interpretation, the interpretation of beta, is a log odds ratio. And there are many other generalized linear models. Others that you will see are listed here. So let's go back to this case control study. And we'll recall that we looked at the odds of vitamin A among deaths divided by the odds of vitamin A among those alive. And our bottom line was that the odds ratio was equal to 0.6. So we'll keep in mind that we have both defined odds of vitamin A among deaths, odds of vitamin A among those alive, and the odds ratio of both. But let's look at this in a different direction. This is a 2x2 table, so there are implicit relationships in a 2x2 table. And we could look, instead of what we did on the previous slide, which was looking at the odds of vitamin A, we could look at the odds of death in the vitamin A group and the odds of death in the placebo group. So the odds of death in the vitamin A group are now looking at the proportion who died in the vitamin A, and that is 46 over 107, divided by the proportion who remained alive, 61 divided by 107. This reduces to 46 divided by 61. If we look at the odds of death in the placebo group, the proportion who died are 74 over 133. The proportion who remained alive are 59 divided by 133. And that reduces to 74 divided by 59. So the odds ratio, taking the odds of death in the vitamin A group of 46 divided by 61, and the odds of death in the placebo group in the denominator, 74 divided by 59, we see that we get an odds ratio of 0.6. So what do we observe? We observe what's known as the property of invariance of the odds ratio. So in other words, we can go back to the previous slide and we see that the odds of vitamin A among deaths divided by the odds of vitamin A among those who remain alive is 0.6. And we also just saw that the odds of death in the vitamin A group divided by the odds of death in the placebo group is also an odds ratio of 0.6. And this property of invariance of the odds ratio will always hold in 2x2 tables. This is a way of looking at it in English. In other words, the estimated odds ratio can be written as the odds of vitamin A among deaths divided by the odds of vitamin A among those who remain alive. And we can see also that the odds of death in vitamin A divided by the odds of death in the placebo group, both will end up mathematically being the same. So now let's go and set up a simple logistic regression model, which is used with dichotomous responses. So implicitly, our outcome has to be binary or dichotomous, taking on one of two values. The covariates or predictors, as you saw in linear regression, can be any quantifiable variable. So it could be a dichotomous covariate, as we saw in the 2x2 table, and we'll use as an example in this lecture, but it could also be a categorical variable or a continuous variable, and that would can be extended for multiple logistic regression. For a simple logistic regression, we're modeling the log odds, and that is what implies a model for our probability. So the function of the expected y that we're using is not the average y or the expected y as we saw in linear regression. Rather, we're modeling the log odds, which is the log of the probability that y equals 1 divided by the probability that y equals 0. We're taking the log base e of that fraction. And then in the fourth bullet, we can write a simple logistic regression as the log odds of the event. And the equivalent ways of framing this are the log of the probability that y equals 1 divided by the probability that y equals 0. But we know that that denominator is the same as 1 minus the probability that y equals 1, because Q is 1 minus P. So log odds equals a straight line relationship with one covariate. So we have beta naught plus beta 1 times our single covariate in a simple logistic regression. What we're going to prove to ourselves is that the regression coefficient, beta 1, is a log odds ratio. We're going to be using log and the natural log, log subscript e, interchangeably in this lecture. So whenever we're using log, it's the natural log, which can also be written as ln, but we'll be using log to represent the natural log. And we'll see that the statistical inferences that we can make with simple logistic regression are what we also saw in linear regression. We can set up 95% confidence intervals for the true underlying regression coefficient beta by taking the estimated beta plus or minus 1.96 times the standard error of that estimate. We can set up a z-test to test the null hypothesis that a regression coefficient beta equals 0. We use a z-test in which our observed z-statistic takes the estimated beta minus 0 divided by the standard error, and we would reject the null hypothesis if this observed z is large and our p-value is less than 0.05. So the regression for our simple logistic regression using this case control study would be that our response variable y is case status, dead or alive. Our covariate x is vitamin A exposure, where we have vitamin A or placebo, and we're interested in the odds of death as a function of vitamin A exposure. So we would write this as the log odds of death, the probability of death divided by the probability of remaining alive, equals beta naught, the intercept, plus beta 1, the slope, times vitamin A. So if we extend this on the next slide to indicating that our logistic regression is one in which the case status is 1 for death and 0 for alive, then our log odds of death equals beta naught plus beta 1 vitamin A. And we would note that 1 will be the value of vitamin A when the child received vitamin A, and 0 would be the value of vitamin A among children receiving placebo. So let's look just among children receiving vitamin A. So that means the covariate of vitamin A has to take on the value of 1. We can plug in that 1 for vitamin A and write the log odds of death equals beta naught plus beta 1. So in short, log odds of death equals beta naught plus beta 1 among children receiving vitamin A. And among children receiving placebo, we would substitute in 0 for vitamin A, and we would be able to write the log odds of death equals beta naught among children receiving placebo. So we'll just recall then the second bullet allows us to say beta naught plus beta 1, the sum of these is the log odds of death among children receiving vitamin A. Beta naught by itself is the log odds of death among children receiving placebo. So let's keep that in mind to go to the next slide to say we can actually subtract these two log odds. And we'll recall that there is a property of logarithms in which the difference between two logs, say log A minus log B, is equal to the log of the ratio. So the log of A divided by B. So that's what we will be doing here. We take the log odds of death among children receiving vitamin A minus the log odds of death among children receiving placebo, and that difference in two log odds gives us the log of the ratio of the odds of death among vitamin A recipients divided by the odds of death among placebo recipients, and that is defined as our log odds ratio. So on the previous slide, we saw that the log odds of death among children receiving vitamin A is beta naught plus beta 1. The log odds of death among children receiving placebo was beta naught, so we'll subtract that. We see that the beta naughts cancel out, we're left with beta 1. And so our interpretation of this regression coefficient, beta 1, it's the vitamin A coefficient, is a log odds ratio of death among those receiving vitamin A compared to that among those receiving placebo. So if beta 1 is a log odds ratio, then taking the anti-log, meaning exponentiating beta 1, gives us an odds ratio. And this is typically what we interpret, the exponentiated coefficient, because the exponentiated beta 1 gives us the odds ratio of death among children receiving vitamin A versus children receiving placebo. So I'm setting this up so that we then can make some interpretations of these coefficients when we run a simple logistic regression model, which we'll do now. And there are a number of different commands that one can use in Stata. The first is the Logit command, where when we're looking at modeling the log odds of death as a linear function, beta naught plus beta 1 times vitamin A, where vitamin A is 1 for vitamin A and 0 for placebo, we can use the command Logit, follow it by the Y variable, which is case status, and then follow it by the X variable, the covariate of vitamin A. We can see that Stata tells us this is a logistic regression. The number of observations is equal to 240, which is what we saw. And then we see the estimated coefficients for beta 1, which we give by B1 as the estimate of beta 1. That coefficient is negative 0.508. It's the log odds ratio of death in vitamin A versus placebo. And we see what is called underscore constant. That's the intercept, which we labeled here as B naught. So B naught is the estimate of the intercept beta naught, and its value is 0.226. And we would call that the log odds of death among those receiving placebo. So I'm going to just extract those coefficients again so that we can interpret these. And if you recall, the log odds of death when x equals 1, so when x equals 1, vitamin A equals 1, the log odds of death is beta naught plus beta 1. And the log odds of death when vitamin A equals 0, which is placebo, is just beta naught. So we can take the difference, and when we took the difference, we saw that's the same as the log of their ratio. So the log of the odds ratio of death in vitamin A compared to placebo is beta 1 itself, which means we're estimating that log odds ratio of comparing odds of death in vitamin A to odds of death in placebo as negative 0.51. So it's a log odds ratio, whereas the estimated intercept, B naught, is a log odds of death among those treated by placebo. And so we're estimating that by 0.23. Now, there's a little bit of a simpler way in Stata to get the exponentiated values, and we'll see that on the next slide. But if our null hypothesis is that beta 1 equals 0, that's the same as saying the log odds ratio, beta 1 equals 0. But think of this as being the same as if we exponentiated both sides of this null hypothesis, beta 1 equals 0, then we would have the exponentiated beta 1 equals e to the 0, which is equal to 1. Or another way of saying this is that the odds ratio is equal to 1. If we exponentiate the log of an odds ratio, we get the odds ratio. If we exponentiate 0, we get 1. So using the Logit command, we get the betas. And we would look at the z-test and the associated p-value and the 95% confidence interval. And we can see that the p-value is greater than 0.05, so we fail to reject. We look at the confidence interval, it overlaps the hypothesized value of 0. So based on this z-test and the 95% confidence interval, there is not a statistically significant association between death and vitamin A status using a significance level of 0.05. So here is the logistic command in Stata. So we can use this to obtain the exponentiated coefficients. So if we say logistic, the y variable is case or death status. Vitamin A is the covariate. We can see that instead of a label that says coefficient, the label of this second column is odds ratio, with a note that the underscore constant, the intercept, estimates the baseline odds. In other words, this estimates the odds of death in the placebo group. So these odds, this column takes the coefficient and exponentiates it. So the exponentiated B1 is the estimated odds ratio of death in vitamin A versus placebo. That's the value of 0.6 that we had calculated by hand. In addition, the exponentiated B0 is the estimated odds of death in the group coded 0 for vitamin A, the placebo group, and that value is 1.25. And if we look back at what we had calculated as the odds of death in the placebo group, it would be 1.25. So let's look at our hypothesis test and confidence intervals using the Logistic Command. Remember that this is the same as the null hypothesis that the exponentiated beta 1 equals 1. In other words, that the odds ratio equals 1. So we look at the z-test and the associated p-value. We look at the 95% confidence interval for the exponentiated beta 1 or odds ratio to see if it overlaps 1, indicating no association. So in fact, the p-value is identical to what we got with the Logit command. It should be, it's 0.052, but the confidence interval is now for the odds ratio, the exponentiated coefficient, and we see that that does overlap 1. So based on the z-test and the 95% confidence interval, we would conclude that there's not a statistically significant association between death and vitamin A status. It's the same conclusion that we got when we used the Logit command that was expressing B1 and B0 as coefficients. In this Logistic command, we have the exponentiated coefficients, which give us the odds ratio of death in vitamin A versus placebo for 0.6, and 1.25 is the log odds of death in the placebo group. So in sum, if we use the Logit command, we're testing a null hypothesis that beta 1 equals 0, which is another way of saying the log odds ratio equals 0. We look at the z-test and the p-value. We would reject that null hypothesis if the p-value was less than 0.05. When we're expressing this as coefficients, though, we look at the 95% confidence interval for beta 1 to see if it overlaps 0. And if it overlaps 0, we would fail to reject the null hypothesis. Using the Logistic command, it's the same as a null hypothesis that the exponentiated beta 1 equals 1. In other words, that the odds ratio itself equals 1. We again look at the z-test, reject it if the p-value is less than 0.05. We look at the 95% confidence interval for the exponentiated beta 1 to see if it overlaps the value of 1. If so, we would fail to reject the null hypothesis. If it does not overlap 1, we would reject the null hypothesis. But whichever command we use, we should reach the same. We will reach the same conclusions. So I've taken you through the case control study in which we have a 2x2 table, a dichotomous outcome and a dichotomous covariate. We needed to make some assumptions that the 240 children in the study were independent. One individual's outcome did not influence the others. We should have performed some model checking, and model checking for goodness of fit of the model to the data can be performed with the Hosmer-Lemeshow test. And we could extend this to include multiple covariates using multiple logistic regression. And that can be done in a separate lecture in which the covariates of interest could be X's which are dichotomous, categorical, or continuous. The outcome, of course, for a multiple logistic regression is still dichotomous. The Y variable of interest is dichotomous. So lastly, in summary, we saw that generalized linear models provide a way to express the linear relationship between a response Y and one or more explanatory variables. So there's a link between the expected value of Y and the straight line relationship. In logistic regression, the link is taking the log odds. In other words, the log of the probability that Y equals 1 divided by the probability that Y equals 0. For a simple logistic regression, we saw that the estimated B1 estimates beta 1, the log odds ratio of the outcome in one group versus another by level of X. The estimated B naught, which is estimating beta naught from a simple linear regression, estimates the log odds of the outcome when X takes on the value of 0. We interpreted the coefficients from a simple logistic regression as well as the exponentiated coefficients, and we looked at the regression statistics in the form of the z-test and the confidence interval to lead us to appropriate conclusions. And we noted that in a 2x2 table, there is a property of invariance of the odds ratio in a simple logistic regression in which the odds ratio of y by the status of X is the same as the odds ratio of X by the status of Y.
With this, we come to an end of the introduction to simple logistic regression. In the next session, Professor Marie Diener-West would be discussing an introduction to multiple logistic regression and then would demonstrate the application of multiple logistic regression on Stata version 16. We hope you enjoyed this session. Thanks for stopping by.